Coulomb's law, or Coulomb's inverse square law, is an experimental law of physics that quantifies the amount of force between two stationary, electrically charged particles. The electric force between charged bodies at rest is conventionally called electrostatic force or Coulomb force. So now, let's talk about vector quantity. The electrical force, like all forces, is typically expressed using the unit Newton. Being a force, the strength of the electrical interaction is a vector quantity. Vector quantity that has both magnitude and direction. The direction of the electrical force is dependent upon whether the charged objects are charged with like charge or opposite charge, and upon their spatial orientation. By knowing the type of charge on the two objects, the direction of the force on either one of them can be determined with a little reasoning. In the diagram below, objects A and B have like charge causing them to repel each other. Thus, the force on object A is directed leftward, and the force on object B is directed rightward. On the other hand, objects C and D have opposite charge causing them to attract each other. Thus, the force on object C is directed rightward, and the force on object D is directed leftward. When it comes to the electrical force vector, perhaps the best way to determine the direction of it is to apply the fundamental rules of charge interaction, using a little reasoning. Electrical force also has a magnitude for strength. Like most types of forces, there are a variety of factors that influence the magnitude of the electrical force. For example, two like charged balloons will repel each other, and the strength of their repulsive force can be altered by changing three variables. First, the quantity of charge on one of the balloons will affect the strength of the repulsive force. The more charged a balloon is, the greater repulsive force. Second, the quantity of charge on the second balloon will affect the strength of the repulsive force. Gently rub the two balloons with animal fur and they repel a little. Rub the two balloons vigorously to impart more charge to both of them, and they repel a lot. Finally, the distance between the two balloons will have a significant and noticeable effect upon the repulsive force. The electric force is strongest when the balloons are closest together. Decreasing the separation distance increases the force. The magnitude of the force and the distance between the two balloons is said to be inversely related. Now, let's talk about Coulomb's law equation. A quantitative expression for the effect of these three variables on electric force is known as Coulomb's law. Coulomb's law states that the electrical force between two charged objects is directly proportional to the product of the quantity of the charge on the objects and inversely proportional to the square of the separation distance between the last two objects. In equation 4, Coulomb's law can be stated as where Q1 represents the quantity of charge on object 1 and Q2 represents the quantity of charge on object 2 and the D represents the distance of separation between the two objects. The symbol K is a proportionality constant known as the Coulomb's law constant. The value of this constant is dependent upon the medium that the charged objects are immersed in. In the case of air, the value is approximately 9.0 times 10 raised to the power of 9 n times m squared over c squared. If the charged objects are present in water, the value of K can be reduced by as much as a factor of 80. It is worthwhile to point out that the units of k are such that when substituted into the equation, the units on charge and the units on distance will be cancelled, leaving a Newton as the unit of force. The Coulomb's law equation provides an accurate description of the force between the two objects whenever the objects act as point charges. A charge-conducting sphere interacts with other charged objects as though all of its charge were located at its center. While charge is uniformly spread across the surface of the sphere, the center of charge can be considered to be the center of the sphere. The sphere acts as a point charge with its excess charge located at its center. Since Coulomb's law applies to point charges, the distance d in the equation is the distance between the center of charge of both objects. The symbols q1 and q2 in the Coulomb's law equation represents the quantities of charge on the two interacting objects. Since an object can be charged positively or negatively, these quantities are often expressed as plus or minus values. The sign on the charge is simply representative of whether the object has an excess of electrons or a shortage of electrons. It might be tempting to utilize the plus and minus signs in the calculations of force. While the practice is not recommended, there is certainly no harm in doing so. When using the positive sign and negative sign in the calculations of force, the result will be that a negative value for a force is a sign of an attractive force, and the positive sign value for force signifies a repulsive force. Mathematically, the force value will be found to be positive when QA and Q2 are like charge, or either both positive sign or both negative sign. And the force value will be found to be negative when Q1 and Q2 are of opposite charge. One is positive sign and the other is negative sign. This is consistent with the concept that oppositely charged objects have an attractive interaction, like charged objects have a repulsive interaction. In the end, if you're thinking conceptually, you will be very able to determine the nature of the force, attractive or repulsive, without the use of positive sign and negative sign in the equation. Our last topic is about comparing electrical and gravitational forces. Electrical force and gravitational force are the two non-contact forces discussed. Coulomb's law equation for electrical force bears a strong resemblance to Newton's equation for universal gravitation. The two equations have a very similar form. Both equations shows an inverse square relationship between force and separation distance. And both equations show that the force is proportional to the product of the quantity that causes the force charge in the case of electrical force and mass in the case of gravitational force. Yet, there are some striking differences between these two forces. First, a comparison of the proportionality constants K versus G reveals that the Coulomb's law constant or K is significantly greater than Newton's universal gravitation constant or G. Subsequently, a unit of charge will attract a unit of charge with significantly more force than a unit of mass. will attract the unit of mass. Second, gravitational forces are only attractive. Electrical forces can be either attractive or repulsive.